afternoon. I'm Simone. I'm a PhD student at the University of Bologna, and today we'll present you our neuromorphic acceleration through register streaming extension or RISC-V course. So, first of all, what is neuromorphic computing? Neuromorphic computing is a computing technology based on spiking neural networks, and there are some key differences with respect to traditional artificial neural networks. First of all, in SNNs, neurons communicate each other by emitting spike, so the input and output tensors are represented by 1 and 0s, and they also incorporate the temporal dimension into their working model. Also, each neuron is represented by an internal state, which is updated at each time iteration of the network, and is called membrane potential, or more simply, P. Also, the activation function of this kind of network is a bit more complex with respect to the traditional ReLU function in INNs, and is called leaky integrate and fire. So, at each time iteration, all the weights associated with an input spike in the input feature will be accumulated. The accumulated value will be then added to the internal state of the output neuron, and then a decay operation is performed, which can be implemented as a simple multiplication by a constant value between 0 and 1. Then a thresholding operation is performed. So if the computed value crosses the threshold, an output spike is generated. Due to the thresholding operation, this kind of networks exhibit a high degree of sparsity in the input and in the output features. And all of these characteristics make them suitable to build event-based perception systems, mainly due to the fact that we can replace the MEC operation with a less energy-hungry add operation, and due to the sparsity, we have a reduced computational workload. So in order to tackle this challenging workload, already many neuromorphic processors have been developed. On the y-axis, you can see the flexibility or the programmability of these accelerators, while on the x-axis, you can see the energy per synaptic operation, which is the energy cost to accumulate one weight. These kind of accelerators can be split into mainly two families, custom analog or digital globally asynchronous or locally synchronous SoCs. And these kind of accelerators are entirely tailored to run only these kind of models. So they are not very flexible, and they are very difficult to program. The second family is made up by custom fully digital accelerators, which at the moment, these kind of accelerators do not provide enough arithmetic support to this kind of network, and also the network topology that you can map on them is very limited. Our work is focused on a fully general purpose architecture. It's called Occamy, has been developed by Pulp Group at ETH Zurich. We also have a sample of the chip at our booth. And is an highly parallel architecture based on clusters of snitch cores, and it provides support for floating point, streaming, and sparse linear algebra computing through its extensions. So here I have an overview of a snitch cluster inside the Occamy architecture. So in each snitch cluster, we have 8 cores, ADMA, used to efficiently transfer the data from the external memory to the tightly coupled data memory, which is a memory that the worker core can access in only one cycle if there is no conflict in the interconnect. Then the cores are snitch cores, so 32-bit. They are tiny cores coupled with a double precision floating point unit, and they are enhanced with 3 SIE extensions. The first one is called Streaming Semantic Registers, and it maps floating point registers directly to memory streams by the use of dedicated address generators and data movers. The access patterns supported are affine, indirect, and sparse. The second extension is called floating point repetition and implements hardware loops over floating point instruction. The third extension is called small float and implements floating point SIMD support down to FP8 format. So our contribution is a kernel library for spiking neural network inference on a snitch-based platform where we exploit snitch SIE extension to accelerate the computation and also to maximize the floating point utilization. So here we have an example of the convolutional layer in an SNN, which is the key bottleneck in the event-based perception system based on these models. So we have the weights, we have the input features, and we adopt a compressed representation for the input features. So each tensor, each vector is compressed into a channel length value, which tells us how many spiking neurons we have in that vector, and a channel index array that tells us which tells us the channel indexes of the spiking neurons in that vector. So by using a compressed format, of course, we can get memory, better utilization of the memory, and we can easily replace the MAC operation with an add operation. However, the compression automatically brings in an indirection operation, and as you can see on the snippet of code, in the hot loop of the sparse convolution, we have only one instruction that actually is a useful instruction. And so this leads to a low floating point unit utilization. So how can we exploit SNitch ISA extensions to accelerate the computation? So firstly, we load the output state of the internal state of the output neuron into the floating point unit. Then we set up the sparse streaming semantic register, so we provide the pointers of the channel index array and of the weights tensor. Then we set up the floating point repetition over an SIMD FAD instruction, and then we start the stream. So the data mover will start fetching the channel indexes, and will provide them to the address generator. The address generator will compute the indirect addresses, and then the data mover again will start streaming the weights directly from the TCDM to the floating point registers. As soon as the weights reach the target register, they will be consumed by the SIMD floating point add operation issued by the floating point repetition sequencer. Once we process the one sub-patch of the whole convolutional patch, we jump to the next sub-patch. And once we computed the whole convolutional patch, we apply the last two instruction of the leaky integrate and fire activation function. By doing so, we perform a sort of layer fusion, so we don't have to rewrite the value back into the external memory. And also, in the hot loop of the sparse convolution, now we have only one instruction that is actually the useful instruction that we want to issue. So then we have 8 cores in a SNitch cluster, so we want to parallelize also the workload. So first of all, we copy the patches using asynchronous DMA copies, and we perform an on-the-fly compressed into raw. So in TCDM we will have a data structure like this one. Then we copy also the weights. Each core then works on each convolutional patch, so on each row of the compressed into raw data structure. And then, in order to mitigate the workload imbalance that we have due to the usage of a compressed format, we implemented a workload stealing mechanisms, while the weights are stationary in TCDM and are broadcasted to all the cores. All the DMA memory transfers are then performed in a double buffered fashion in order to hide the memory latency of the external memory. So here we have our some preliminary results of our optimized library. So we take a kernel 14 by 14 by 256, which is a key kernel in a spiking VGG model, and we run tests using QuestaSim, so a circular query simulator, and we computed the speed up and the floating point utilization of our optimized version with respect to the baseline. For moderate levels of sparsity, we can reach a speed up factor of 6, while for high levels of sparsity, so above 80%, the speed up factor is a bit reduced due to the fact that we don't have a lot of values to work on, and we're issuing a lot of DMA requests. Regarding the floating point unit utilization, the baseline is very low, so it's around 10%, while the floating point utilization of our optimized version is, for moderate levels of sparsity, again, around 60%, and above 80% it decreases for the same reasons why the speed up factor decreases. So in conclusion, we proposed a kernel library for spiking neural network, the first on RISC-V systems. In particular, we targeted a snitch-based platform where we exploited all its IC extension to accelerate the workload and to maximize the floating point utilization. We also preliminarily evaluated our method on a kernel taken from a spiking VGG model, and we set the different sparsity levels. Our optimized version always outperforms the baseline, and power simulation, end-to-end deployment, and comparison with the neuromorphic processors are now ongoing. Thank you for the attention. If you are interested, I will be on Thursday at the poster session.
Yes. Any questions for Simone and about his paper here and the work that he's been doing on this? Neuromorphic stuff? Okay. Hello? Is there? Okay. Thank you again, Simone.
Thank you.